Can you see the class assignment number 6?
Yes, Doctor, we can see.
Okay, so we are going to start. Just check whether it is recording. Yes, it's recording. So we are going to start the first question. What we need to do here, using 16 bits, we have to represent the following two numbers using sign and magnitude representation method. So we have to use the first representation method for an integer number. As you know that integer number are represented in a different way than a character type data. Character types are represented in computer memory using their ASCII values. So ASCII values are converted to a binary, and that is the way how a character type data is stored in computer memory. But integer type data are stored in computer memory in different way. For example, one of the method is sign and magnitude representation method. So we'll use the sign and magnitude representation method for representing the number to minus 26,155. This is a negative number. And as you know that sign and magnitude representation, what we do, the leftmost bit we use for the sign. The leftmost bit we use for the sign. So what we have to do, for the negative number, we know the negative sign represented using 1, and positive sign is represented using 0. So since our first number is a negative number, so I'm putting the leftmost bit, which is basically for representing the sign. So that's the sign bit. So we are putting 1 there because our number is a negative number. So I'm putting sign in the leftmost bit. So remaining bit we'll use for representing the 26,155. So at first what I would like to do is to, for each bit, each remaining 15 bits, I would like to first generate the positional value for each bit. Any question, anyone?
Yes, Doctor. The first row
Yes.
for what? Why
First, okay, first row is for positional value. That's exactly what I'm going to say now. So first row, I will show each positional value for each bit. For example, the first positional value is 1. That's the 1 for the positional value for the first bit. And second positional value is 2. Third positional value is 4. Then it is 8. Then it is 16. Then it is 32. Then it is 64, then it is 128, then 256, then 512, and 1024. So it looks like that we need more space, so I'm just reducing the size of the this font. Okay, 1024, then 2048, then 4096, then 8192, and then 16,384. So basically, these are positional value basically calculated based on the base of the binary number. So the first digit, which is digit number 0, to the power 0 is equal to 1. Then to the power 1 equal to 2, to the power 2 equal to 4, to the power 3 equal to 8. That is the way how we calculate a positional value. So here, in order to represent the number value 26,155, first we need to know each of the bits and their corresponding positional value. Once we know the positional value, we can select the bits which are appropriate to get our 26,155. So basically, we are going to use a calculator, but you can see that 16,384 should be taken because our number is 26,155. So I have taken 16,384. Then definitely we can take the second one as well because 8,192. So 16,000 plus 8,000 is 24,000. So we can easily take 8,192. So I'm taking that one as well. But how much we have got so far? 16,003, sorry, 16,384 plus 8192, uh, sorry, 16,384 plus 8,192 is 64,576. So we got 24,576. Still, we need some more values. So 4,000 cannot be taken because 4,000 plus 24,000 is 28,000. But our number is 26,000. So we need to put 0 here. Definitely, we may take 2048. Any question? Anyone wants to ask
Hello,
any
doctor.
question?
The first
Yes,
the first one on the left is for the sign.
for the sign, because the method that we are going to implement here is sign and magnitude. And you know the sign and magnitude, you have to always use the leftmost bit as a sign bit. Remember, this is a sign and magnitude representation. The leftmost bit
Yes.
should be used for the sign. And since our number is negative number, so you must put the 1 for the negative sign. Is it clear?
Oh, yes, clear.
Okay.
Doctor,
So now we, yes.
can we write the minus 32,000 on the last bit on the first column? Yes, please.
You can write that one, but usually in sign and magnitude representation method, we don't write minus 32,768 because that bit is actually the sign bit, so we just keep it as a sign. But in two's complement representation, yes, we'll put that sign. Yes,
Okay, thank you.
the positional value with negative number. Is it clear to everyone?
Yes.
Thanks for asking the questions. So 24,576 we have already done. We have not taken 4096, so we are going to take 2048. So if we take 2048, I think it will be more than 26,155.
We can
So we
take
can,
2,000 because it's more than.
yes, yes, yes. So we cannot take 2048, but rather we can take 1024. So if we take 1024, the value is 25,600. Still, we are smaller than 26,155, so we can take that one. And I think we can also take 512. So 25,600. I think we can also take 512. So if we take 512, uh, it will be 26,112. So we can easily take 1 here. Definitely we cannot take 256. We cannot take 128 because our number is 26,112 already, and this is 26,155. So we are less than, I think, 43. 43. We need 43 more. So we don't need 64, but we can take 32 definitely. And we don't need 16, so we can put 0. So 32 plus 8 is 40, so we can take 40, and we can take 42 and 43. So I think that is done. So if I add 43 to it, so if I add 43 to it, then 26,155. So you can see this is the exact representation for minus 26,155 in sign and magnitude representation. Remember, this is sign and magnitude representation method. So in same way, we are going to solve the same the other problem, that is 12,588, but that's a positive number. That's not a negative number. So in that case, again, we can put the same positional value. You can see that I'm copying the positional value and I'm pasting the positional value. So once the positional value is there, uh, everyone, is it all right? Can I go to the next one?
Yes, clear.
Yes,
Yes.
no problem.
Clear.
Okay. Okay, thank you. So our next problem is positive number 12,588, and you can see that we can easily put 0 here. If we put 0 here, you can see that it's a positive number. So as I told you that the leftmost bit should be used for the sign. So since it's a positive number, so it should be 0 here. So 0 represent the plus sign and 1 represent the minus sign. So in this case, we are putting 0 in the leftmost piece of the 16-bit. Now we have the number, the magnitude is 12,588, but our first positional value is 16,384. So we are putting 0 as well, but definitely we can take 8192. So I'm putting 1 here. So I'm opening the calculator again. So
And you can take 4,000 also.
yes, we can take 4,000. I think 8192 plus 4096. That is 12,288. So we are left with exactly 300. Can you see that? 12,588, but we have got 12,288. So we can take 2048.
265. So.
Yes, we will get, we are left with 300. As I told you, we are left with 300 after taking 2048. Sorry. We have taken 4096. It's not it. But we did not take 2048. I'm sorry for that. So this is 8192 and 4096. These two numbers, two positional value we have taken, and because of that it is 12,288, and we are left with exactly 300. So we don't need 2048, we don't need 1024,
yes.
We don't need 512, but we can take 256. And we don't need 128, we don't need 64, but we can take 32. So if we take 32, this is 256 plus 32. So we are adding 256 plus 32. We are left with, I think, 12, 576, 588. So we are left with 12. So we can make it 12 easily.
Take 8 and
8
4.
and 4. Yes, exactly. Exactly 8 and 4. We'll take 8 and 4. So both are 1 and remaining will be 0. So this is the end of our sign and magnitude representation for two numbers. You have seen that in case of sign and magnitude, we always use the leftmost bit as a sign bit, and remaining bits are used for representing the magnitude. Now we'll solve a problem used for same integer representation, but we'll use a different representation method that is called 2's complement representation method. This is a method actually widely being used in most of the computer architecture all over the world. So basically 2's complement representation method, we know one thing common between 2's complement and sign and magnitude, that if the numbers are positive number, then 2's complement representation and sign and magnitude both are their representation basically same. But in case of 2's complement representation, what we do, we have a positive number. You can see that we have a positive number first, 107 using 8 bits. So I have 8 boxes here. So what we'll do, we'll put the positional value. First positional value is 1. Then second positional value is 2. Then 4. Anyone having any question that how do we calculate the positional value? Anyone having this question? Anyone having this question that how do we calculate the positional value?
No, thank you.
No, thank you. Okay, so this is the first position value is 1, second position value is 2, third position value is 4. Third means basically 2 to the power 2 is 4. Our position values position basically starts from 0. This is 0th position, so 2 to the power 0 is 1. This is 1 position, 2 to the power 1 is 2. This is 2 position, 2 to the power 2 is 4. This is position number 3, that is 2 to the power 3 equal to 8. Then it is 16. Then it is 32. Then it is 64. Sorry,
64. And minus 128.
Minus 128. That is exactly what we do, especially when it is a it is a 2's complement representation. Remember, always we'll use a negative positional value when it is a 2's complement representation. You can see that the leftmost bit, we have made it a positional value which is a negative positional value. The other positional value is basically as usual. So since our numbers is a positive number, so again we'll do the same thing. We don't need the negative positional value, so we'll put 0 there, and the remaining values we have to make 107. So in order to make 107, we can definitely take 64.
And
So we
32.
put and definitely 32. So 64, 32, basically 96.
We don't need 16.
We don't need 16. We can put 0 there.
We can
And
take
this
8.
is 8. So because we are
And
left with 11, and we don't
0.
need 4, but we can take
1, 1.
2 and 1. Yes. So 64 plus 32 is 96, plus 8 is 104, plus 3 is 107. So this is the exact representation for 2's complement representation using 8 bits for 107. Remember one thing, that if you use the sign and magnitude representation, the same representation, there is no difference between the 2's complement representation and sign and magnitude when the number is a positive number. But just the method is a little bit different. We use the positional value, but usually in case of sign and magnitude, we don't take the positional value negative. So this is the one. Is there any question here? Can we go to the next topic?
Clear.
Clear. Okay, so the next number is minus 10,258. Anyone, any question? Okay. So the next number is minus 10,258. So minus 10,258 using 16 bits. You can see that I have 16 boxes here, but you might say why we have 4 rows. The first row we'll use basically for positional value. Since we already have some positional value already, I'll just copy and paste that one. So positional value. This is our positional value, and now this is a negative number, so the last one is a 2's complement representation, so last one should be minus 32,768. So 32,768. Okay, so this last one is basically our positional value is negative. The remaining positional values are positive. So since our number is a negative number, minus 10,258, so what we have to do, we have to take minus 32,768, or that is one method that we can directly take minus 32,768 and then add some positive numbers to get minus 10,258. So when the numbers are big, in that case, the safest way is that you just represent plus 10,258, and then you just flip it and then add 1 to it, and you get the result. I think we need one more. I'm not sure whether you can make extra boxes. There's no way. So what I'm going to do, I'm going to put 0 here. Because now we are basically representing plus 10,258. So we'll put 0 here as well. We can take 8192. So 8,192, we are taking it because we are trying to represent now 10,258 plus 10,258. That is the safest way of representing any negative number in 2's complement representation method. So definitely we will not take 2096, so we'll put 0 there. If we take 2048, I think we can take 2048. So 8192 plus 2048, 10,240. We are almost there, so we can take 2048, and this is 10,240, but our number is 10,258. We are left with 18, so we don't need 1024, we don't need 512, we don't need 256, we don't need 128, we don't need 64, we don't need 32, but we can take 16 because we are left with 18. So I'm taking 16 and 0, 0, and 1 and 0. Anyone trying to ask me any question?
No,
Because
no.
I can't see. Okay, so I can't see your board. I'm completely on Word. Um, if I share the screen, the Blackboard screen and the Word screen, then it will be smaller for you. So I'm just full screen with Word, so I don't see what is happening in the Blackboard. Anyway, so um, this is the representation for 10,258 plus. So in order to convert it to minus 10,258, what you have to do, each bit will be flipped. So 0 will become 1, 0 will become 1, 1 will become 0, 0 will become 1, 1 will become 0, 1 will become 0 will become 1, sorry, 0 will become 1, 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 and 1 will become 0, 0 will become 1, 0 will become 1, 1 will become 0, and 0 will become 1. So you can see that every bit we have flipped. So 0 becomes 1, 0, 1, 1, 0, 0, 1, 1, 0, 0 become 1, 0 become 1, 0 becomes 1, 0 becomes 1, 1, 1, 1, 0, 0, 1, 0, 1, 1, 0, 0, 1. So we are going to add 1 to it, and if we add 1 to this number, 1 to this number, so 1 plus 1 is 0. We are left with carry equal to 1, so that 1 plus 0 is basically 1, and that's it. The remaining bit will be just copied. Remaining bit will be just copied. So I'm copying that one. So that's the actually simplest method of representing any negative number in 2's complement representation method. You can do that, or as I told you, that you can take any, in case of negative number, you take the negative positional value, which is the smallest value, and then add some positive value to make it bigger as per your requirement. So as many positive value as you need to get your desired negative number. So that is another way of doing it, but this is the straightforward. There is very less chance of making a mistake, and less calculation is required. That's why usually people like this one when you have a bigger number, not a number less than 100. When a number is big, and a number of bits you are using also big, in that case it's better to use this particular method. Any question, anyone?
No, doctor. That's clear.
Okay,
Doctor,
good. Now,
so
yes,
both way is correct, right?
both ways correct. You can do in any one of the way. I have
Okay.
no problem if you do in any one of the way. But you must show me how did you get the result. Okay. So if you work with minus 32,768, then the addition that you have done, you should show me the addition. Are you understanding? Because with this one you have added some values, so you should do show me that addition. Whether you are doing it using calculator, but still you show me that how you have got these values. Okay. Or if you do it in this method, this is clear that the steps are you are showing, so you don't need to show me anything. Anyway, so this is the question number 3. Perform the following addition operation. Assume that the numbers are represented in 2's complement representation method using 8 bits. So we need to perform some addition operation. But before we can perform the addition operation, actually we need to represent these numbers using using how many bits? 8 bits.
Doctor,
Uh, yeah, I think it's
in our paper
is
is
it 8, 6? Is it 11 or 12 bit?
12 in our paper.
12. Yeah, actually this is the file that I updated in the college. When I was in the college, I updated and then printed for you. But this is my at home version of the file, so I could have to update it here. So this is 12 bit actually. So thank you for reminding me. So this 12 bits, we are going to use 12 bits. You can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, one extra bit. So is it you have also 12 column or 13 column? How many columns you have?
Yes,
12.
12.
12.
12. Okay, exactly. Good. So here also what we are going to do, we first represent 1255, then we represent 514, then basically we'll add them together. How many rows are there? 3 rows or 4 rows?
3.
3 rows. So I'm not showing the positional value. What we are going to do, first we represent 1255. You know that 1255 actually without positional value difficult. Uh, so I'm just making extra rows. So this is 1. You can just put write the positional value there. You can write the position value on the top of the row. So this is 1, 2. We can copy. I think it's 2048 up to that. Yes. So this is a positive number, and this is 2's complement representation. Um, the last one is negative number, minus 2048. So, but we are not going to take minus 2048 for 2's complement. We'll take 0. 1024, definitely we can take that one. We don't need 512, so I am putting 0 there. We cannot take 256 because if you see that if we take 256, so it is 1024 1024 plus 256, which is, sorry, 1024 plus 256, 1280, but our number is 1255, so we cannot take 256 as well. So I'm putting 0 there, but we can definitely take 128. Any question, anyone? So this is, we have done 1024 plus 128, which is 1152. Can you hear me?
Yes.
Yes.
And now we
Yes, we
can
can hear
have
you.
64 and 32.
Yes, we have now, we can take 64 definitely. We can take 32. Um, so
7 remaining.
plus 64 plus 32 is 1248. We are left with 7. So we don't need actually 16. We don't need 8, but we need 7. So 1, 1, 1. So 4 plus 2 plus 1 is 7. So that's actually 1255 in 2's complement representation method. This is the representation of 1255. Now we are going to represent 514. So again, this is a positive number, so I'll put 0 here. We don't need 1024, so I'll put 0 here. We don't need, we need 512, sorry. So we can put 1 there, and it is 514. Our value is 512. So already we got 512. So just we need two more. So put 0, 0, 0, 0, 0, 0, 0, and 1 here, then 0 here. So that's the one. Now we are going to um, add our values. 1255 plus 514, both are positive number, and we are doing addition. So 1 plus 0 is 1. 1 plus 1 is 10, that is 2. 1 plus 1 is 2, which is represented in binary is 10. So we'll put the value 0, and remainder is 1. That carry, not remainder, sorry, carry is 1. So carry 1 plus this one is basically again 2, which means we'll put 0, and our remainder is, sorry, not remainder, carry is 1. So we'll put 1 here. 0 plus 0 again 0. 1 plus 0 is 1. 1 plus 0 is 1. 1 plus 0 is 1. 0 plus 0 is 0. And 1 plus 0 is 1. 1 plus 0 is 1. And 0 plus 0 is 0. So that is the addition of 1255 plus 514. You can check later on whether this is the correct representation of the addition of these two numbers. Definitely the addition of these two numbers are 1255 plus 514, 1769. So you can check later on whether this number represents 1709 or not. Is it okay, everyone?
Yes, clear.
Clear.
Okay, now I'm going to take sorry, not 5 minutes, 2 minutes break, and then we'll come back and we'll start the question number 4, and we'll do the question number 5 both. So just give me 5 minutes break, then I'll come back and we'll start again. Can we start now?
Yes.
Yes.
Okay, so now the question number 4, we are going to start the question number 4. Um, you can see this is a subtraction operation, as I told you in the class as well, that in most of the architecture actually we design the microprocessor in such a way so that our subtraction operation can be performed actually by doing some addition operation. So in this particular problem, you can see that we need to do subtraction, but actually we can convert it in such a way so that we don't need to do the subtraction. What we'll do, we'll represent minus 125, and then we'll add it with minus 45, So we are going to add. It's not basically we are going to subtract. Rather, we are going to add two negative number. One is minus 125, another is minus 45. So these two negative number, we are just going to add, and that way we'll perform the subtraction operation. Is it clear to everyone?
Clear.
Yes.
So Okay, so instead of doing the subtraction, we are now going to do the performing the addition operation, but we need to represent minus 125, and since we need to represent minus 125, so what we have to do, we have to make our positional value can't do anything. We need another one, but you can put it positional value on the top. Okay, so so and to bring back single column. Yeah. Oh, this actually we cannot do it here. We need to go here. So minus 125. So in order to represent that one, we need to put the position value 1, then 2, then 4, then 8, then 16, then 32, then 64, then minus 128. Now, since this is minus 128, just do something. Okay. So this is minus 125, so we can easily take minus 128. If we take minus 128, we need to add 3 more to minus 128 so that we can get minus 125. By the way, if we do that, in that case, we don't need to actually flip. We are directly representing the number, so we don't need any one of them. But if you want to represent minus 125, in order to represent minus 125, you can represent it as plus 125, and then flip it and then add 1 to it. You can do that one, or you can directly represent this one. So here, are you understanding what I'm saying?
Yes.
We can directly represent minus 125. In that case, we don't need to do anything else. Are you understanding? We don't need to do anything else in this slide because there are 2 tables here. You can see one table is for representing minus 125, another table is for representing minus 45. But since these are the smaller number, so we can directly represent them. And in that case, I don't need the remaining boxes. So this is 128. Plus we need to add 3 to it. So 1 plus 1. Everyone understanding?
Yes, doctor, it's clear.
That what we have done here, why we are not using other boxes, because we are not representing plus 125, then flip it and then add 1 to it to get minus 125. We are representing minus 125 directly. So this is the one we have taken the positional value, minus positional value, which is 1 minus 128, then we have added 3 to it, so it becomes minus 125. The same way we can take this positional value for the next one, so we can directly get their representation. Okay, now again minus 145, so we can take one, that is 128 minus 128. We can take 64, so 128 plus 64 is minus 64. Minus 64, but our number is minus 45, so we cannot take 32. sorry, we cannot take 32, but we can take 16. So 64 plus 16. 64 plus 16. So 64 plus 16 is basically 48, minus 48, but we are still, our number is minus 45. So we can take 16, then we need to add 3. So if we add 3, then it will become minus 45. Are you following? This is minus 128 plus 64 is minus 120, minus 64. Minus 128 plus 64 is minus 64. Then if we add again 16 to it, so it's a minus 48. Then if we add 3 to it, then it will be minus 45. So that is actually how we represent minus 45. This is minus 125. So these two representation, I'm going to copy them here. We are going to copy them here. This is minus 125 and this is minus 45. I'm copying them here now, and now we are adding them. Now we are going to add them together. So 1 plus 1 is 10, so we'll put 0. Carry is 1, so that carry 1 plus 1 plus 1 is 3. 3 means 1 1, so we'll put 1 here, and again carry is 1, so that 1 plus 0 is carry is still 1. So this 0 plus 0 is 0, then 0 plus 1 is 1, and then 0 plus 0 is 0. 0 plus 1 is 1, then 1 plus 1 is 0. We'll discard the 1. Now you see that there is some problem happen here. Can anyone tell me what is the problem?
Yes, doctor.
Dot is in positive.
The sign.
You can see that we are adding two negative number and we got the result positive, is not it? What is the
Yes,
problem?
overflow, doctor.
It's overflow.
It's an overflow error because the number minus 125 and minus 45, if you add them together, the result that we'll get is 125 minus 45. So minus 170 cannot be represented using 8 bits. That's the problem. Because it cannot be represented using 8 bits, that's why we got the result which is a positive result. When you are adding two negative number and you are getting the result as a positive result, that is indication that this number 170 minus 170 cannot be represented using 8 bits. And how do you know that? Because we got a positive result. So an overflow error has been occurred. Why an overflow error occurred? Because we got a positive number, and we know that when you are adding two negative number, if we get a positive number, that means an overflow error occurred. But our job is done. We can go to the next problem, question number 5. Can we go to the question number 5?
Yes, doctor. You
Yeah.
can.
So we'll do this one as the last one, inshallah. So this is a multiplication operation. In order to remind you, I just want to tell you that we are going to use the Booth's algorithm. That's the Booth's algorithm. In case of Booth's algorithm, we know that Booth's algorithm is capable to perform the multiplication with sign and unsigned number. We have already seen in the slide that there is a method where we can perform unsigned multiplication. That is a easier method. But if you want to work with a signed number, that means you can have one positive number, one negative number, or you can have both negative number, or you can have both positive number. In that case, you can use the Booth's algorithm, and using this Booth's algorithm, we can perform the multiplication with any number of bits. Now in this particular problem, you can see that we are multiplying two numbers. One is number 13, another is number 11, and you can see that number 13 can be represented using number 13 is our multiplicand. Number 13 is our multiplicand, which is m, and number m is 13, which can be represented using 5 bits. So 8, this is 1 plus 4 is 5 plus 8 is 13. So multiplicand is m, which is equal to 13, and this is the representation for the multiplicand. This is minus 11, and you know that minus 11 is second one is our multiplier. Multiplier is q, and multiplier can be also represented using 5 bit. So you know that multiplier minus 11, so this positional value is 16, minus 16 positional value, plus if you add 5 to it, then minus 16 plus 5 is minus 11. So this is a 2's complement representation of minus 11. And as we know that we have to have a additional register, register A, which will contain our final result. And as we also know that when you are multiplying one 5-bit number with another 5-bit number, what will be the result? Result will be 5-bit or result will be 10-bit? Anyone? Can anyone answer that?
bit.
So remember one thing, when you are multiplying a 8-bit number with another 8-bit, the result will be 16-bit, not 8-bit. Or if you multiply a 5-bit number with another 5-bit, the result will be 5 plus 5 is 10-bit. So our result will be stored basically in the one extra register, which is A, and in UQ. So basically our final result will be stored in A and Q, but A will contain the most significant 5-bit and Q will contain the least significant 5-bit. Are we understanding?
Yes, it's
Are we
clear.
understanding?
Yes.
It's clear. So the final result will be stored in the register A and register Q. But remember, Q is basically now containing your multiplier, and multiplier is also 5-bit, and your multiplicand is also 5 bits, which is 13. And we know that sometimes we may need to calculate A minus M, and A minus M means basically we are going to add A plus minus M. So that's why m dot, which is basically minus 13, and this is minus 13 means 16 plus 3 is minus 13. So this is a representation of minus 13 because sometimes we need to perform a minus m. Now, as you know that in this Booth's algorithm, your a will be first initialized to 0, then your q is whatever you have multiplied, that is your q, and q minus 1 is basically also initialized to 0. Just like your a is initialized to 0, your q minus 1 will be also initialized to 0, and this is your multiplicand. It will be constant. It is not going to be changed. So multiplicand will be remain as it is, but we are going to change the value in a. We are going to change the q because a and q together collectively will contain our final multiplication result, and q minus 1 will be initialized to 0 initially, and it will be changed every time. So these are the initial value. Is there any problem? Anyone can do I need to remind you what we need to do every time, every iteration? Since we have 5 bits, we will have total 5 iteration. We'll have 5 iteration. We'll have 5 iteration. So this is total 5 iteration. You can see that there are total 5 iteration because our multiplicand is 5 bits, multiplier is 5 bits. So each iteration, what we have to do, we have to check what is the value of q and q minus 1. If q and q minus 1 both are 0, 0 or both are 1, 1, In that case, we'll just perform a arithmetic right shift operation. Arithmetic right shift operation if both least significant bit of q and q minus 1 both are 1 1 or both are 0 0. But if the q is 1 and q minus 1 is 0, then we'll perform a subtraction operation, that is a minus m, and result will be stored in a. But if q is 0 and q minus 1 is 1, that is 0 1, in that case we'll add the we'll perform an addition operation, that is a will be added with m. Are we following?
Yes, but in Q we see the less significant or the most significant.
In q we'll always work with the least significant bit.
Okay.
Are you understanding? So do you want me to go back to our algorithm? Do I need to show you the algorithm?
For me, it's clear.
Okay. You can see that. Can you see that? Can you see that if your
Yes.
q0 and q minus 1, if they are equal to 1 1 or they are 0 0, if they are 1 1 or 0 0, in that case we just need to perform the arithmetic shift right. As I told you, and I will show you what is arithmetic right shift. We'll explain that one. Arithmetic right shift will be done when q0 and q minus 1. q0 means least significant bit of q, and q minus 1, if they are both 1 1 0 0, in that case we'll perform arithmetic shift operation. But if they are 0 1, then we'll perform the addition operation with a will be added with multiplicand. But if they are 1 0, then m will be subtracted from a, result will be stored in a. After, whether we go in this path or we go in this path, but in both cases we have to also perform the arithmetic shift operation. And then we'll check how many times we have performed this iteration. If we have a 5 bits number, your iteration will be also 5 bits. Is it clear to everyone? Can we go back now? Can you go back now?
Doctor, you can go back.
Okay. Now you see that because our least significant bit of q and least significant bit of q minus 1 both are 1 0, so we are going to perform a subtraction operation. That means m will be subtracted from a. Now let's see what is our a. A is basically 0 0 0 0, and what is our m? Because it's a minus m. Since a minus m result will be stored in a, so minus m means we are basically add with minus m, which is minus 13, 1 0 0 1 1. So you can see that our values are 1 0 0 1 1. This is minus m. So this is a, this is minus m. So it will be added together, and we'll finally get the result is 0 plus 1 is 1, 1 plus 0 is 1, 0 plus 0 is 0, 0 plus 0 is 0, 1 plus 0 is 1. That's the result of a minus m, and result will be stored in a. Are you understanding? Any question, anyone? So far our q will remain as it is, our q minus 1 will remain as it is, and definitely our m will remain as it is in each iteration. So m is not going to be changed, but q and a is going to be changed, and q minus 1 will be changed. So you can see that a has been changed already from 0 0 0 0 0 to 1 0 0 1 1. In that iteration, will not change anything in q and q minus 1. Are you understanding?
Doctor,
Yes.
why we are not changing anything in Q? We are saying that we are shifting Q right shift, right?
No, shifting, we have not done shifting. First, we will perform a minus m. That is the first step we have done. Now we'll do the shifting. Arithmetic right shift. Are you following?
Yes.
As you know that, again, go back to our, can you see the algorithm, or should I make it bigger?
We can see.
So you can see that whether we do a minus m or a plus m, after doing any one of these operation, we have to also do the arithmetic right shift. So first we have done a minus m because 1 and 0, q0 was 1 and our q minus 1 was 0. So since this is the combination, we have to do the subtraction, that is m will be subtracted from a, result will be stored in a, and then after that you can see that from here we have to do the arithmetic right shift. Are you understanding? Any question? So we have just done a minus m. A was 0, 0, 0, 0. Minus m is basically minus 13. So we'll add minus 13, which is 1, 0, 0, 1, 1, 1, 0, 0, 1, 1. That is our minus 13, which is minus m. And then we are going to add them together because we know that we cannot perform any subtraction. So instead of doing the subtraction, we are adding minus m to a, which is basically doing the subtraction. So that is our value after doing the subtraction. Q will remain as it is, q minus 1 is 0, m is as it is, and now we'll perform the arithmetic right shift. Now how to do the arithmetic right shift? As I told you, that in case of arithmetic right shift, this one will come here, it will remain as it is, but this one will be shifted to the right here. So 1 has been shifted here and 1 is remain as it is in the leftmost bit. Are you understanding? That's the main characteristics of arithmetic right shift, where every bit, not every bit, the leftmost bit will remain its a sign. So that means sign bit will remain as it is. So your 1 will stay here and then 1 will be shifted to the right. Then since 1 has been shifted here, so 0 will be shifted here, this 0 will be shifted, this 0 will be shifted here, this 1 will be shifted here, this 1 will be shifted here, this 1 will be shifted here, this 0 will be shifted here, 1 will be shifted here, this 0 will be shifted here, and this 1 will be shifted here. Is it clear?
Yes,
Arithmetic
doctor.
right shift.
That's clear.
Again, in case of arithmetic right shift, the leftmost bit will remain as it is, and it will be shifted as well to the right, and this one will shifted here, 0 will be shifted here, 0 will be shifted here, 1 will be shifted here, 1 will be shifted here, this one will be shifted here, this 0 will be shifted here, this 1 will be shifted here, this 0 will be shifted here, and this 1 will be shifted here. So first iteration done. Any question, anyone?
No, doctor,
Anyone?
it's clear.
Okay, now we'll do the second iteration, and in order to do the second iteration, again we have to check what is the value of q0. Q0 means least significant bit of q, and this is q minus 1, this is 1. So 0 and 1, we know that when this combination is 0 and 1, we need to do the addition operation. So the operation will be addition, that is a equal to a plus m. Our m will be remain as it is. So this is our a now. So this is our a now. After finishing of the first iteration, this is our current value of a. So this is 1 1 0 0 1. This is our current value of a, and our m is, we know that m is 0 1 1 0 1. So you can see that our m is 0 1 1 0 1 0 1 1 0 1, and then this is our final value after adding a plus m. This is our a, current value of a. This is our m. So 1 plus 1 is 0, carry is 1, 1, 0 plus 0 is 1, then 1 plus 0 is 1, 1 plus 1 is 0, carry is 1, so that 1 and this 1 will make it 10, 10 means 0, and carry is 1, that will be discarded. And this is our value, which is 0 0 1 1 0, that's our value. And our q will remain as it is, your q will remain as it is, and our q minus 1 will remain as it is, m will remain as it is. We have just performed a equal to a plus m, and we know that whether you do a equal to a minus m or you do a equal to a plus m, you have to do the arithmetic right shift. So this is our arithmetic right shift. Sorry. So what will happen? This 0, this is our a, so 0 will remain here as a sign bit, and then 0 will be shifted here, then this 0 will be shifted here, this 1 will be shifted here, this 1 will be shifted here, this 0 will be shifted here, this 1 will be shifted here, this 1 will be shifted here, 0 will be shifted here, this 1 will be shifted here, this 0 will be shifted here. So we have done the arithmetic right shift. After doing the arithmetic right shift, that is the end of our step number 2. Then we'll go to the iteration number 3. Then again, in iteration number 3, we have to check what is our least significant bit for q, which is 1, and q minus 1 is 0. So when it is a combination is 1 and 0, we have to perform the arithmetic, we have to perform a equal to a minus m. So a equal to a minus m, we have to perform. This is our a, and our minus m, we know that our minus m is 10011. So this is our a is 00011, and this is our m, which is 10011. So minus m, sorry, that's our minus m, 10011 minus m. So a and plus minus m will actually give you the actual result of subtraction. So a equal to a minus m. Minus m is 10011. So this is our a, which is 00011, and now we have to perform the addition operation. Once we do the addition operation, this 1 plus 1 is 0, or carry is 1. Then 1 plus 1 plus 1 means we carry 1 is 1 1, that is 3. So we have to put 1, still carry is 1. So 0 plus 0 plus 1 is 1, and we don't have any carry. So 0 plus 0 is 0, and 0 plus 1 is 1. So that is after finishing a equal to a minus 1 m. This is our a value, will remain q as it is, and our q minus 1 will remain as it is. But as you know that we have to, whether we do a equal to a minus m, we have to do the arithmetic right shift now. Now how to do the arithmetic right shift? This 1 will remain here as 1, and this 1 will be shifted here. 1 0 will be shifted here, 1 will be shifted here, 1 will be shifted here, 0 will be shifted here, 0 will be shifted here, 1 will be shifted here, this 1 will be shifted here, 0 will be shifted here, and this 1 will be shifted here. So we have done the arithmetic right shift. Same way, we have to do the step number 4, and in order to do the step number 4, we have to again check 0 and 1. This is the least significant bit of q, and this is q minus 1, which is 0 and 1. When it is 0 and 1, we have to perform the a equal to a plus m. So we need to do a equal to a plus m. This is our a. So here this is our a, 11011, and our m is, that's our multiplicand, which is 01101. So 01101, that is our m. This is our a. So we'll add them together. 1 plus 1 is 0, carry is 1. That 1 and this 1 is again 10. 0, carry is 1. That carry 1 and this 1 is 10. 0, carry is 1. 1 carry, this 1 and this 1, total 1 1. So this is 1, carry is 1. So 1 and this 1 is 10. So that is 0, and the remaining 1 carry 1 will be discarded. So this is our, after addition, a equal to a plus m. This is our addition. Q will remain as it is, q minus 1 will remain as it is. But now we have to perform arithmetic shift, arithmetic right shift we have to do. So 0 will remain here, 0, and 0 will come here. Then this 1 will come here, this 0 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 will come here, this 1 will come here, this 1 will come here, this 0 will come here. So that's our arithmetic shift. And now final step number 5, where we'll get our result of multiplication. So again, we have to check what is our value of Q0, which is least significant bit of Q multiplier. So this is 1 and 0. As we know, if it is 1 and 0 combination, it is a subtraction. So we'll do the subtraction now. So equal to a minus m. So this is our a, which will come here as it is. Minus m is basically minus 13, 10011. So we'll put 10011. So we'll add them together. 0 plus 1 is 1, 0 plus 1 is 1, 1 plus 0 is 1, 0 plus 0 is 0, 0 plus 1 is 1. So after addition, that is our new value of a. This is q, remain as it is, q minus 1 remain as it is, and this is our multiplication. Now we'll do the again arithmetic right shift. After performing the arithmetic right shift, we'll get our final result. So this one will remain here as it is, 1 will be shifted here, 0 will be shifted here, 1 will be shifted here, 1 will be shifted here, 1 will be shifted here, 0 will be shifted here, 0 will be shifted here, 0 will be shifted here, 1 will be shifted here, and this one will be shifted here. So your final result, this is your most significant 5 bits, and this is your least significant 5 bits. If you combine them together, you'll find this value is basically minus 13, sorry, plus 13 multiplied minus 11, which is minus 143, and this value combinedly, this value is minus 143. If you check at home, you'll find this is minus 143. So that is the end of our class today. Inshallah, on Saturday we'll work with the addressing mode, and we'll also solve one class assignment on addressing mode, but we'll definitely take a little bit of time on addressing mode. I have to explain you the previous things as well as the 2 more addressing mode. I will explain, and then we'll solve the class assignment. Inshallah, we'll be able to do that. If you have any question, you can ask me now.
Doctor.
Yes.
I have
Yes.
question. And in step 4, we add
Yes.
a plus m. A is 11011. Okay, but
Yes.
but
And m is our multiplicand. M is multiplicand, which is 0, 1, 1, 0, 1, 0, 1, 1, 0, 1. We just added them together.
okay.
Is it clear to everyone?
Thank you, Doctor.
Thank you. So I will upload the video maybe 1 hour later, because it takes some little bit of time to prepare the video, and I will upload the video in both sections, inshallah. So if you have not done yet, you can check the video and you can solve your class assignment and submit it on Sunday, inshallah. If I don't
Thank you very much.
no problem. If I don't upload, still you already know how to solve it. So I will upload, inshallah, as soon as possible. So I'm stop sharing and stop the video. How many students join here? Total 35. That's fine, not bad. So I'm stop